Picture this: a ghostly atmosphere stretching 696,000 kilometers across space. That's not the diameter of a star or a gas giant. It's the invisible envelope surrounding a truly extraordinary visitor, perhaps the most extraordinary our solar system has received in decades. Right now, as you listen to these words, Comet 3 Atlas is racing toward the Sunday. It's dragging behind it a carbon dioxide atmosphere so enormous it could swallow our entire star. The Spherex Observatory has mapped this spectral giant, revealing a coma. That's the technical term for a comet's fuzzy atmosphere. An atmosphere extending at least 348,000 kilometers in every direction. Do the math, and you're looking at something roughly half the sun's diameter in width. But here's where it gets interesting. This isn't some blazing inferno you could spot with backyard binoculars. The comet's nucleus, its actual rocky heart, remains frustratingly small and dim. Hubble's best estimates place it at no more than 5.6 kilometers across. That's smaller than Manhattan. Yet somehow this cosmic pebble is generating an atmosphere 55 times wider than Earth. The question that's keeping astronomers awake at night is simple. How is this even possible? And more unsettling still, what does this impossible visitor reveal? What does it tell us about the terrifying scales on which our universe truly operates? Stay with us as we unravel the mystery of 3 Atlas, because what we've discovered about this ancient wanderer will change how you see the cosmos forever. To understand how something so small can create something so impossibly large, we need to look closer. We need to see what 3 Atlas is actually made of. The answer lies hidden in its alien chemistry. While most comets were familiar with spew water vapor when the sun's heat reaches them, 3 Atlas decided to be different. It's belching carbon dioxide at a rate that would make a soda factory jealous. And carbon dioxide, unlike water, starts sublimating at much colder temperatures. It turns directly from ice to gas. This means 3 Atlas began its atmospheric show while still incredibly far from the Sunday. It was building that half-sun-wide envelope we're witnessing today. Think of it as the solar system's most extravagant magic trick. A tiny performer creates an illusion so massive it defies our understanding of scale. The coma isn't solid, of course. It's more like cosmic fog, a tenuous collection of gas molecules. Molecules expanding into the vacuum at speeds that would liquefy any earthly atmosphere. But its sheer size creates problems we've never had to solve before. Take photography, for instance. When astronomers try to capture 3 Atlas, they're shooting through the densest star fields in our galaxy. The comet's trajectory carries it across the Milky Way's most crowded regions. This turns every observation session into an exercise in stellar hide and seek. Images streak with star trails as telescopes track the comet's motion. They create pictures that look more like abstract art than scientific data. The carbon dioxide shows up best in infrared light. It's invisible to our eyes, but crystal clear to specialized detectors. In these wavelengths, 3 Atlas resembles a glowing soap bubble drifting through space. Its edges are so faint they blur into nothingness. The visible coma, what you might actually see through a telescope, is much smaller. It's perhaps only 26,000 kilometers across. Still massive by Earth standards, but a mere fraction of the infrared monster lurking beyond. This disconnect between visible and invisible scale should make us uncomfortable. How many other cosmic phenomena are we missing? Missing simply because we're looking in the wrong wavelengths. How many half-sun-wide atmospheres have drifted past unnoticed because they don't glow in the colors our ancestors evolved to see? The carbon dioxide envelope tells us something profound about the origins of 3 Atlas. Most solar system comets are water-rich. This reflects the conditions where they formed in our sun's protoplanetary disk. But a comet this rich in carbon dioxide suggests something else. It suggests formation in a colder, more distant environment, perhaps around a different star entirely. We're not just witnessing a large coma. We're seeing evidence of alien chemistry literally. As 3 Atlas continues its approach toward its October encounter with the Sun, its atmosphere should grow. That already enormous envelope should become even larger. More heat means more sublimation, more gas production, more expansion. The half-sun-wide envelope we see today might be just the beginning. But here's the truly unsettling part. The size of the coma determines how the comet interacts with the solar wind. That's the stream of charged particles constantly flowing from our star. A bigger atmosphere means a bigger target. It means more dramatic interactions, more opportunities for the kind of space weather that can disconnect comet tails, or create spectacular light shows millions of kilometers long. The stage is set for a performance measured not in theaters or stadiums, but in astronomical units. 3 Atlas isn't just visiting our solar system, it's transforming a region of space larger than our Sun into its personal laboratory. And we're all invited to watch, to see what happens when half a sun's worth of atmosphere meets the full fury of a star at solar maximum. A hyper-fast ancient traveler. Speed kills, they say. But in the case of 3 Atlas, speed reveals. This isn't just another comet lazily orbiting our Sunday, not some cosmic commuter on a predictable schedule. 3 Atlas is moving at 68 kilometers per second at its closest approach. That's fast enough to cross the continental United States in less than 2 minutes. That's hyper-fast by solar system standards. And it tells us something extraordinary. This visitor will never return. The mathematics are unforgiving. 3 Atlas follows what astronomers call a hyperbolic orbit. This means it's gravitationally unbound from our solar system. Once it swings around the Sun this October, it will accelerate back into the interstellar void. It will travel at 58 kilometers per second, never to be seen again. In cosmic terms, we're witnessing a one-night stand, a brief encounter between our solar system and a wanderer from elsewhere. But where is elsewhere exactly? Trace the trajectory of 3 Atlas backward through space and time. You will arrive at a startling conclusion. This comet originated from the direction of Sagittarius near the galactic center. It's been cruising through interstellar space for potentially billions of years, carrying with it the chemical fingerprints of whatever stellar neighborhood birthed it. The age estimates are staggering. Multiple analyses suggest 3 Atlas belongs to the thick disk population of our galaxy. These are ancient stars and debris with orbital characteristics that scream, "I was here first." Some studies bracket its age between 3 and 11 billion years. Others push that estimate beyond 7.6 billion years. This makes the comet potentially older than our entire solar system. Let that settle for a moment. The rocky nucleus of 3 Atlas, no bigger than a small city, may have formed long ago. It could have formed when our Sun was nothing more than a diffuse cloud of gas and dust. It watched our galaxy evolve through cosmic epochs we can barely imagine. It survived stellar explosions, gravitational perturbations, and the slow churn of galactic dynamics. All of this eventually ejected it from whatever system gave it birth. Think of 3 Atlas as a time capsule wrapped in ice and rock. It preserves chemical conditions from an era when metallicity was lower, a time when stellar formation followed different rules. The thick disk population represents the galaxy's middle age. This was a time when star formation was more violent and less organized, a very different environment from the one that produced our Sunday. This ancient heritage explains why 3 Atlas behaves so differently. Its carbon dioxide-dominated chemistry reflects formation conditions we don't see in our local neighborhood. The ice compositions, the dust-to-gas ratios, even the way it responds to solar heating, all of these bear a unique signature, a signature of a different time and place. The journey itself beggars comprehension. For millions or billions of years, 3 Atlas drifted through the cold between the stars. Its surface was perhaps occasionally stirred by cosmic rays or the faint pressure of starlight. It passed through the outer fringes of other stellar systems. It witnessed the birth and death of stars, and it slowly tumbled through the galaxy's spiral arms like a message in a bottle, a message thrown into an ocean of vacuum. What finally brought it to us? Probably nothing more dramatic than chance. The same gravitational lottery that occasionally sends asteroids on Earth-crossing orbits. The same chance that flings planets into interstellar space. Our solar system simply happened to intersect its trajectory at precisely the right moment in cosmic history. The encounter timeline reads like a precisely choreographed dance. Perihelion is on October 29th, at 1.36 astronomical units from the Sunday. That's closer than Mars, but not by much. A near miss of Earth at 1.8 astronomical units in December. Close enough for excellent observations, but far enough to pose zero threat. And perhaps most intriguingly, a series of planetary encounters. These will provide multiple opportunities to study how an ancient wanderer behaves, how it acts under modern solar system conditions. But here's what should give us pause. 3 Atlas represents just one data point in what must be an enormous population of interstellar objects. Current models suggest millions or billions of these cosmic refugees are drifting through space right now. They are invisible and undetected until they happen to wander close enough to a star, close enough to warm up and announce their presence. We're not just observing a comet, we're glimpsing the debris field of galactic evolution itself, the scattered remains of countless star systems that have lived, died, and ejected their children into the void. 3 Atlas is simultaneously a visitor and a messenger. It carries news from stellar neighborhoods so distant and ancient, their very existence challenges our provincial view, a view of cosmic chemistry. The terrifying scale isn't just about size, it's about time and distance and the sheer improbability of this moment. An object older than our world, moving faster than anything in our experience, has chosen this brief moment. A moment in cosmic history to grace us with its presence. When it leaves us behind in 2026, it will carry our measurements with it. It will carry our curiosity and our wonder into the dark between the stars. A living, electrified atmosphere. Forget everything you think you know about empty space. The region around 3 Atlas isn't empty. It's a bustling factory of plasma physics, electric fields, and magnetic drama. A drama playing out on a scale that makes earthly lightning look like static electricity. That half-sun-wide atmosphere isn't just passive gas, expanding into a vacuum. It's what physicists call a dusty plasma. A complex soup of electrically charged particles, tiny grains, and magnetic field lines, all interacting in ways that would make any laboratory jealous. The moment sunlight and the solar wind hit the comet's coma, they begin a transformation. They turn neutral gas molecules into ions, creating a vast electrified atmosphere, an atmosphere around that tiny nucleus. Picture this. As carbon dioxide molecules sublimate from the comet's surface, they encounter the sun's ultraviolet radiation. They become ionized, stripped of electrons, and left with positive electric charges. These newly created ions don't just drift peacefully into space. They couple with the solar wind's magnetic field. They get swept up and accelerated along magnetic field lines that stretch back to the sun itself. This is how comet tails form, not from rocket exhaust or atmospheric friction, but from the gentle yet inexorable pressure of magnetized plasma flowing from our star. The ion tail of 3 Atlas will point directly away from the Sunday. This is regardless of the comet's direction of motion, like a cosmic weather vane responding to magnetic field lines invisible to our eyes. But here's where 3 Atlas gets interesting. Its retrograde orbit carries it almost directly opposite to the direction planets normally travel. More importantly, this path will take the comet across the heliospheric current sheet. This is a vast wavy boundary in the solar wind where magnetic field polarity reverses. Think of the current sheet as the galaxy's largest windsock. a surface that flutters and ripples as the sun rotates every 27 days. When comets cross this boundary, their plasma environments can change dramatically. Magnetic field reversals can kink tails or create disconnection events. They can even generate entirely new structures in the coma. The European Space Agency's Rosetta mission gave us our first intimate look at these phenomena. It studied the plasma around Comet 67P. Even that relatively quiet comet developed a surprisingly dynamic ionosphere. It had electric fields, accelerating particles, and plasma waves propagating through the coma. 3 Atlas, with its massive atmosphere, should provide a natural laboratory, a lab for studying these effects on a much grander scale. And we're approaching this encounter during solar maximum, a time when our star's magnetic field is at its most chaotic. Coronal mass ejections are more frequent and more violent during these periods. These are billion-ton blobs of magnetized plasma hurled from the sun's surface. When a CME slams into a comet's atmosphere, the results can be spectacular. We might see compressed Comet restructured tails and sometimes complete tail disconnections. This happens as magnetic field lines reconnect and release enormous amounts of stored energy. The plasma physics gets even more complex when you consider dust. 3 Atlas is shedding microscopic particles along with gas, and these tiny grains become electrically charged in the solar wind environment. Charged dust behaves very differently from neutral material. It can be accelerated by electric fields or trapped in magnetic bottles. It can even be organized into complex structures by plasma instabilities. Some of these dust grains are submicron water ice crystals detected by JWST. Others are likely rocky debris from the nuclear surface. Each grain becomes a tiny spacecraft carrying electric charge. It responds to the complex electromagnetic environment surrounding the comet. The result is a 3-dimensional sculpture of charged particles, a sculpture constantly shifting and evolving as the comet moves. We need to be careful about cause and effect here. Comets don't trigger solar flares or coronal mass ejections. They're simply unlucky victims when these events occur. But they do serve as exquisitely sensitive probes of space weather conditions. The way the tail of 3 Atlas kinks disconnects or brightens tells us something. It tells us more about the solar wind structure than any spacecraft could measure directly. Current sheet crossings are particularly important. They often coincide with high-speed solar wind streams. These are regions where the solar wind velocity jumps dramatically. These stream interaction regions create compression waves that propagate outward from the Sunday. And when they encounter a comet's atmosphere, they can create remarkable displays of plasma physics in action. The electromagnetic drama isn't just academic. Mars orbiters might catch glimpses of 3 Atlas during its October 3rd flyby. This could provide our first direct measurements of how the red planet's thin atmosphere responds, how it responds to the comet's charged particle environment. These observations could reveal if large cometary atmospheres can influence planetary magnetospheres, influence them at distances previously thought to be safely remote. What we're witnessing around 3 Atlas is essentially a natural particle accelerator, an accelerator operating at astronomical scales. Magnetic field lines stretch and snap like rubber bands. They release energy that accelerates ions to incredible velocities. Electric fields build up and discharge across distances measured in Earth diameters. And all of this electromagnetic fury is centered around a nucleus smaller than most asteroids. The living, breathing plasma atmosphere of 3 Atlas represents one of nature's most exotic states of matter. It's a state played out against the infinite backdrop of interplanetary space. It's a reminder that the universe is far more electrically active than our earthbound experience suggests, and that even the emptiest regions of space can become theaters for physics so dramatic it challenges our understanding. What 3 Atlas is and isn't. Let's address the elephant in the solar system. Every time an interstellar object shows up, the internet explodes. It explodes with speculation about alien probes, techno-signatures, and extraterrestrial surveillance. So before we dive deeper into the genuine mysteries of 3 Atlas, let's establish some facts. Let's see what we're actually dealing with. 3 Atlas is the 3rd confirmed interstellar object and the 2nd interstellar comet. It follows in the footsteps of the enigmatic 1 Oumuamua and the more conventional 2 Borisov. But unlike Oumuamua, which sparked endless debates, 3 Atlas displays every characteristic of a natural comet. It has a coma, it has gas and dust production. It responds to solar heating exactly as physics predicts. The safety question first. 3 Atlas will never come closer than 1.8 astronomical units to Earth. That is roughly 168 million kilometers away. That's more than the distance from Earth to the Sunday. This places it firmly in the interesting but harmless category. Mars gets a much closer encounter, but even that represents 19 million kilometers of comfortable buffer. So what makes 3 Atlas special isn't danger. Its chemistry, scale, and timing. The comet's carbon dioxide-dominated atmosphere represents an extreme we've never seen before. Its enormous coma challenges our understanding of how small nuclei can generate such massive gas production, and its arrival during solar maximum provides a once-in-a-lifetime opportunity. An opportunity to study interstellar plasma physics under the most active conditions. The natural comet signatures are unmistakable across multiple observatories. Hubble sees the classic fuzzy coma structure. JWST detects the spectroscopic fingerprints of sublimating ices. SPHERICS maps the extended carbon dioxide envelope. Ground-based telescopes track the predictable brightening as solar heating increases. Every measurement points to the same conclusion. This is a dirty snowball from another star system. A snowball behaving exactly as dirty snowballs should. But let's acknowledge the elephant's cousin. The chemistry of 3 Atlas is genuinely weird. That 8:1 carbon dioxide to water ratio is highly unusual. It sits 6.1 standard deviations above typical comet compositions. In statistics, anything beyond 3 sigma is considered highly unusual. 6 sigma events are supposed to happen once in a billion observations. Either 3 Atlas represents an incredibly rare statistical fluke, or its formation environment was radically different. Different from anything we see in our local stellar neighborhood. The scientific method demands we pursue the most exotic hypothesis only after exhausting conventional explanations, and there are plenty of conventional ways to create a carbon dioxide-rich comet. Formation beyond the carbon dioxide frost line, where temperatures are cold enough to freeze it. Heavier radiation from a massive star during the comet's youth, or an insulating crust that preferentially releases carbon dioxide. Each explanation carries implications for understanding planet formation around other stars. If 3 Atlas formed in the outer regions of its birth system, it tells us something. It tells us about the structure and chemistry of alien protoplanetary disks. If it experienced heavy stellar irradiation, it constrains the type of star that could produce such chemistry. If crustal evolution is responsible, it reveals how billion-year journeys might alter comet surfaces. The nucleus itself remains frustratingly elusive. Hubble's upper limit of 5.6 kilometers in diameter could hide a much smaller nucleus, a nucleus as small as 0.3 of a kilometer across. That uncertainty spans 2 orders of magnitude in mass. This makes it impossible to calculate precise gas production rates or predict future behavior. We're essentially studying a comet by its shadow, inferring the properties of an invisible core from the atmosphere it creates. Some early size estimates suggested much larger nuclei, perhaps 46 kilometers across, based on near-infrared flux measurements. But these calculations depend heavily on assumptions about surface reflectivity. assumptions that may not apply to interstellar objects with alien chemistry. The Hubble imaging constraint remains our most reliable measurement. It doesn't depend on assumptions about albedo or composition. Public interest in interstellar objects creates a challenging environment for scientific communication. Every observation gets scrutinized for signs of artificial origin. Every unusual measurement spawns speculation about extraterrestrial technology. The scientific community has learned to present findings with extra caution, clearly separating established facts from preliminary interpretations. This caution serves everyone well. Extraordinary claims about technosignatures require extraordinary evidence, and that evidence simply doesn't exist for 3 Atlas. The comet's behavior falls comfortably within the range of natural phenomena, even if it represents an extreme example of those phenomena. But natural doesn't mean boring. 3 Atlas offers us a direct sample of interstellar chemistry, a billion-year-old time capsule from the galaxy's thick disk population. It's carrying information about star formation conditions that predate our solar system's existence. It's demonstrating plasma physics on scales we can't reproduce in any laboratory. It's providing our first opportunity to study how ancient alien ices respond to modern solar heating. The real mystery isn't whether 3 Atlas is artificial. It's how nature managed to create something so extreme that it challenges our understanding of what's possible. Sometimes, the most profound discoveries come from finding familiar phenomena pushed to extremes, pushed so far that they force us to revise our basic assumptions about how the universe works. 3 Atlas is a natural comet, but it's a natural comet operating at the very edges of what nature apparently allows, and that might be even more interesting than any artifact could ever be. The Interstellar Proof, July 1st, 2025. The Atlas Survey Telescope in Chile captures something unusual in the constellation Sagittarius, just another faint smudge against the star-crowded background of our galaxy's central regions. The initial designation reads like Cosmic Alphabet Soup A11PL3Z. Nothing in that string of characters hints at the extraordinary nature of what was just found. 24 hours later, everything changes. The Minor Planet Center issues a circular. And suddenly, that anonymous smudge has a name and a destiny. C, divided by 2025 N1 becomes 3 Atlas, the third confirmed interstellar object in human history. The I designation isn't awarded lightly. It means NASA's orbital dynamicists have calculated a hyperbolic trajectory, a trajectory that places this object's origin firmly outside our solar system. The mathematics are brutal and beautiful. An orbital eccentricity of 1.047, meaning the trajectory is a perfect hyperbola. A velocity at infinity of 58 kilometers per second, fast enough to escape the sun entirely. These numbers don't lie, and they don't leave room for interpretation. 3 Atlas is a visitor, not a resident. But July's discovery represents just the end of the beginning. Astronomers immediately begin scanning archival images. They search for earlier sightings that could extend the observational arc and refine the orbital solution. These recoveries are like forensic evidence. They allow scientists to trace the comet's path through space with increasing precision. Each additional observation point tightens the mathematical constraints on the origin and destination of 3 Atlas. The announcement ripples through astronomical networks with remarkable speed. NASA's Planetary Defense Coordination Office issues a public statement. It confirms the interstellar nature and emphasizes the safe flyby distance. At 670 million kilometers from Earth at the time of discovery, it poses no threat, but it offers unprecedented scientific opportunities. Educational outreach kicks into high gear almost immediately. Astronomy websites rush to explain the difference between interstellar and dangerous. They help the public understand that an exotic origin doesn't equal an existential threat. The messaging is crucial because interstellar objects tend to trigger both fascination and fear. First images from ground-based telescopes reveal the challenges ahead. 3 Atlas appears as a faint, fuzzy star against the dense background of the Milky Way. Tracking the comet's motion requires exposures that streak the surrounding stars. This creates images that look more like cosmic abstract art than scientific data. The Virtual Telescope Project and other amateur networks begin their own observation campaigns. They contribute to the global effort to characterize this visitor. The Hubble Space Telescope soon enters the game. Its sharp vision cuts through atmospheric turbulence to place the first meaningful constraints on the nucleus size. The result, no larger than 5.6 kilometers across, establishes 3 Atlas as a small but extraordinarily active comet. The ratio of coma size to nucleus diameter exceeds anything seen in our solar system. Meanwhile, JWST begins preparing its own observation campaign. The world's most powerful space telescope will bring unprecedented capabilities to bear. It promises detailed chemical analysis of the coma composition. These observations will provide our first direct measurements of interstellar ice chemistry. They will reveal whether alien comets follow the same formation rules as our local population. The discovery timeline illustrates how modern astronomy operates as a global network. Atlas detects, the Minor Planet Center processes and distributes, major observatories plan follow-up campaigns, and amateur astronomers worldwide contribute additional observations, all within weeks of discovery. 3 Atlas becomes one of the most closely watched objects in the solar system, but the orbital solution continues evolving as new observations arrive. Each measurement slightly adjusts the calculated trajectory. It refines our understanding of where 3 Atlas came from and where it's going. The hyperbolic nature of the orbit never changes. That fundamental conclusion emerged clearly from the first few nights of observations. But the precise orbital parameters keep shifting as systematic errors are corrected. This process highlights a crucial aspect of astronomical discovery. Initial measurements are always preliminary, and responsible science communication must acknowledge uncertainty while still conveying excitement. The interstellar origin of 3 Atlas was certain within days of discovery, but details like the exact perihelion date required weeks or months to nail down precisely. Archive searches extend the observational record back into May and June, back to a time before Atlas made its official detection. These recovery observations are crucial for determining the comet's exact trajectory and timing. They also reveal that the comet was already developing a measurable coma months before discovery. This is consistent with carbon dioxide sublimation beginning at large distances from the Sun. The confirmation process follows strict international protocols. Protocols developed over decades of asteroid and comet discoveries. The Minor Planet Center collects observations from multiple sites and calculates preliminary orbits. It issues circulars only when the trajectory is certain. For interstellar objects, additional scrutiny ensures that measurement errors don't lead to false claims. 3 Atlas passed every test. Its hyperbolic orbit appears in calculation after calculation, refined and confirmed by observations from dozens of telescopes worldwide. The velocity measurements align with theoretical predictions for the interstellar object population. The trajectory traces back to a plausible region of our galaxy's thick disk. This is consistent with kinematic models of stellar populations. By the end of July, 3 Atlas had transformed. It went from an anonymous sky survey detection to a confirmed interstellar visitor. The discovery represents just the first step in what promises to be an 18-month observation campaign. A campaign spanning from now through the comet's departure in late 2026. We've identified our target. Now the real science begins. chemistry at terrifying scale. When JWST turned its near-infrared spectrograph toward 3 Atlas, it revealed something remarkable. Something that should make every planetary scientist pause and reconsider what they thought they knew. The numbers are stark, unprecedented, and frankly a little unsettling. A carbon dioxide to water ratio of 8:1. 6.1 standard deviations above the normal range for solar system comets. Let that sink in. In statistics, 3 sigma events are rare, 4 sigma events are extraordinary. 6 sigma events are supposed to happen roughly once per billion observations. Either we've witnessed an astronomical lottery ticket, or 3 Atlas represents chemistry, so exotic it demands a complete revision. A revision of our understanding of comet formation. The JWST observations paint a detailed picture of alien ice composition. Carbon dioxide dominates at 4.3 micrometers. Carbon monoxide appears at 4.7 micrometers. Water vapor shows up at 2.7 micrometers, but as a distinctly minor component. And scattered throughout the spectrum are the signatures of fine water ice grains. Grains less than 1 micrometer across, suspended in a coma dominated by carbon-bearing volatiles. Spherics independently confirms this chemical weirdness. It mapped the extended carbon dioxide envelope across its 696,000 kilometer diameter. The convergence of results from 2 completely different approaches eliminates any possibility of error. 3 Atlas really is that carbon dioxide rich. But why? The leading hypotheses read like a menu of exotic formation scenarios. Perhaps 3 Atlas formed beyond the carbon dioxide frost line in its birth system. A place where temperatures dropped low enough for CO2 to condense directly from gas into solid ice. This would require formation at distances where most protoplanetary disks are thought to be too sparse. Alternatively, heavy stellar irradiation during the comet's youth might have preferentially removed water. This would leave carbon dioxide trapped in protective ice matrices. This scenario demands a formation environment near a massive luminous star, the kind of stellar neighborhood that would subject forming planetesimals to intense radiation. The third possibility is more subtle but equally significant. Surface evolution during its billion-year journey through interstellar space. Cosmic ray bombardment, micrometeorite impacts, and the gentle pressure of interstellar radiation could have created an insulating crust, a crust that preferentially releases carbon dioxide while trapping water vapor beneath the surface. Each explanation carries profound implications for our understanding of planet formation across the galaxy. If 3 Atlas formed in the outer regions of an alien disk, it constrains the mass and temperature of those systems. If stellar irradiation is responsible, it tells us about the violent environments where some planetary systems take shape. If crustal evolution is the key, it reveals how billion-year journeys through the void might alter small bodies. The production rates derived from JWST spectroscopy are staggering. Conservative estimates suggest 3 Atlas is currently losing several tons of material per second, with carbon dioxide accounting for the vast majority of that mass loss. Picture a freight train's worth of ice sublimating into space every minute, expanding the coma at velocities approaching 1 kilometer per second. But here's what makes 3 Atlas even more unusual. This extreme gas production is happening at 3 astronomical units from the Sunday A distance, where solar system comets typically show minimal activity. Most of our familiar periodic comets don't begin serious outgassing until they get much closer. 3 Atlas is already operating at peak efficiency, while still farther from the Sun than Mars. The spectroscopic signatures also reveal OCS carbonyl sulfide. This molecule requires specific formation conditions. It tells us about the sulfur chemistry in the comet's birth environment. The detection suggests complex carbon-sulfur-oxygen chemistry during the comet's formation. This possibly indicates sulfur-rich ice condensation in a different kind of disk. Comparing 3 Atlas with 2 Borisov reveals the chemical diversity of alien planetary systems. Borisov showed unusually high carbon monoxide abundances. 3 Atlas pushes the carbon dioxide abundance into completely uncharted territory. Each interstellar comet samples different formation conditions, different stellar environments, different galactic epochs. The JWST observations are scheduled to continue post-perihelion. This will allow astronomers to monitor how the comet's chemistry evolves as solar heating changes. These follow-up measurements will reveal whether the carbon dioxide dominance is intrinsic to the nucleus, or if it results from preferential release due to surface effects. Media coverage of the chemical results has been generally accurate, but occasionally sensationalized. Headlines about alien chemistry capture public attention, while sometimes obscuring the careful scientific work. The peer review process for JWST results ensures that published findings meet rigorous standards, but preprint servers allow preliminary results to circulate before formal publication. What's particularly striking about the chemistry of 3 Atlas is how it simultaneously confirms and challenges our understanding. The basic physics of ice sublimation works exactly as expected. Carbon dioxide sublimates at lower temperatures than water. This explains why the comet became active so far from the Sunday. But the extreme abundance ratios push this familiar physics into completely unexplored territory. The chemical fingerprint of 3 Atlas reads like a message from an alien world, a message encoded in molecular vibrations and preserved in ice for billions of years. Each spectral line carries information about temperatures, pressures, and elemental abundances. Information from a stellar system so distant its very existence was unknown until now. We're not just studying a comet, we're conducting archaeology on a galactic scale, using chemistry to reconstruct the conditions that prevailed when our galaxy was younger, when star formation followed different rules. How big is the nucleus, what we know versus the debate? The nucleus of 3 Atlas presents us with a frustrating mystery. An object simultaneously too small to see clearly and too active to ignore. The Hubble Space Telescope, humanity's sharpest eye in space, can only give us a limit. It tells us the solid core measures no more than 5.6 kilometers across. It could be as small as 0.3 of a kilometer in diameter. That's an uncertainty spanning 2 orders of magnitude in mass. NASA's official summary maintains that conservative upper limit 5.6 kilometers maximum diameter. This number emerges from careful point spread function modeling. This is where astronomers attempt to subtract the bright fuzzy coma from Hubble images. The process is like trying to photograph a birthday candle flame while subtracting the glow. Technically possible, but fraught with systematic uncertainties. The challenge stems from the comet's extraordinary activity level. Most comets at this distance show minimal coma development, making nucleus detection relatively straightforward. But 3 Atlas is already surrounded by that massive carbon dioxide envelope. It creates a bright background that completely overwhelms the much fainter reflected light from the nucleus. Early estimates suggested dramatically different sizes. Some analyses based on near-infrared flux proposed nuclei as large as 46 kilometers across. These calculations attempted to work backward from total brightness to nucleus size. They made assumptions about albedo and dust production that may not apply to interstellar objects. The controversy highlights a fundamental problem in comet science. Nuclear size determination depends heavily on assumptions about surface properties we can't measure directly. A dark nucleus reflects less sunlight, requiring a larger diameter to produce the same brightness. A bright nucleus achieves that same brightness with a smaller diameter. Without independent constraints on surface reflectivity, size, calculations become educated guesswork. Hubble's imaging constraint sidesteps most of these assumptions. It directly attempts to detect the nucleus as a point source against the coma. The 5.6-kilometer upper limit emerges from the telescope's resolution limits and from the brightness ratio between the nucleus and the surrounding gas. If the nucleus were larger than this limit, Hubble should have detected it as a resolved object. But even Hubble's measurement carries significant uncertainties. The modeling requires precise knowledge of how the telescope's optics spread starlight. Small errors in this calibration can propagate into large errors in the size limits. Additionally, if the nucleus has an extremely dark surface, it might remain undetected. Undetected even if it's larger than 5.6 kilometers. The size uncertainty cascades into every other aspect of the science of 3 Atlas. Gas production rates, surface composition models, and activity predictions all depend on knowing the nuclear surface area. A 3-kilometer nucleus has roughly 100 times less surface area than a 30-kilometer nucleus. This implies dramatically different sublimation physics to achieve the same gas production. This uncertainty reveals something profound about cometary activity. We tend to think of comets as simple, dirty snowballs, where larger objects naturally produce more gas and dust. But 3 Atlas demonstrates that the relationship can be far more complex. A small but highly active nucleus might indicate unusual ice composition or efficient heat transfer. It could also indicate surface structures that maximize sublimation area. The size debate also illustrates how different measurement techniques can yield conflicting results. Photometric methods analyzing total brightness work well for typical comets. Direct imaging methods excel when the nucleus is large enough and separate from its coma. But 3 Atlas occupies an uncomfortable middle ground where neither technique provides definitive answers. Perhaps most frustratingly, the size uncertainty affects our ability to predict future behavior. Will the gas production continue increasing as the comet approaches the Sun? Will the coma grow even larger? Or will depletion effects begin limiting activity? The answers depend critically on how much ice remains in the nucleus and how efficiently it can sublime under increased solar heating. Comparative analysis with other comet nuclei provides some context. Halley's Comet, probably the most famous, measures about 11 kilometers across. It produces spectacular displays when active. If 3 Atlas really is only 3 to 5 kilometers in diameter, its current activity is remarkable. It suggests either much more efficient ice sublimation or radically different surface properties. The albedo assumption problem exemplifies a broader challenge in astronomy. Inferring physical properties from limited observational data, we can measure how much light 3 Atlas reflects. But translating that measurement into size requires assumptions about its surface. Interstellar objects with billion-year exposure to cosmic radiation might develop unique surface properties. Recent advances in thermal modeling offer potential solutions. By observing 3 Atlas at multiple infrared wavelengths, astronomers can separate thermal emission from reflected sunlight. This provides independent constraints on nuclear size that don't depend on albedo assumptions. These techniques work best for objects with measurable thermal emission. They require observations as 3 Atlas gets closer to the Sunday media coverage of the size of 3 Atlas has sometimes conflated different measurements. It has reported coma diameters and nucleus estimates as if they were comparable quantities. Science communication faces the challenge of explaining this difference, explaining why astronomers can measure a huge atmosphere but remain uncertain about a tiny nucleus. The answer lies in the fundamental difference between extended bright objects and compact faint ones. Ground-based telescopes continue monitoring 3 Atlas as it approaches perihelion. They search for any changes in brightness or morphology that might provide additional clues. Amateur astronomers with modest equipment can contribute to these observations. This demonstrates how citizen science complements professional research. What emerges from this size uncertainty is a reminder that astronomy often proceeds through gradual refinement rather than definitive breakthroughs. The 5.6-kilometer upper limit represents our best current constraint, but it's certainly not our final answer. As the comet's geometry changes and new observations accumulate, that uncertainty should narrow. The nuclear size mystery also highlights the unique scientific value of interstellar objects. Every measurement we make of 3 Atlas must be interpreted without decades of previous observations or detailed knowledge of its formation conditions. We're essentially learning comet physics from scratch, using an object whose properties may differ fundamentally from everything in our experience. When 3 Atlas completes its flyby and heads back into interstellar space, it will carry its secrets with it. Our window for resolving this mystery spans just 18 months. The clock is ticking, the telescopes are watching, and somewhere in that blazing coma lies a nucleus whose true dimensions will determine how we understand this visitor. 2 faces of size: optical versus infrared. The tale of 3 Atlas is really a story about seeing the invisible, measuring the unmeasurable, and discovering that size is a far more slippery concept than most people realize. When we ask how big this comet really is, the answer depends entirely on the light you use. In visible light, the same wavelengths our eyes evolved to detect, 3 Atlas appears as a fuzzy star. It is roughly 26,400 kilometers across. That's about 2 Earth diameters. Impressive by terrestrial standards, but fairly typical for an active comet. Ground-based telescopes capture this optical coma as a compact, relatively dense cloud of dust and gas, but switch to near-infrared wavelengths and 3 Atlas transforms. It becomes something utterly different. Spherics and JWST reveal a gossamer envelope of carbon dioxide, an envelope stretching at least 348,000 kilometers in every direction, 696,000 kilometers across. Roughly half the diameter of our Sunday same comet, same moment in time, but an entirely different definition of size. This isn't measurement error or instrumental bias. It's physics. Different molecules emit and absorb light at different wavelengths. This makes them visible or invisible, depending on which part of the electromagnetic spectrum you examine. The optical coma traces dust particles and certain gas species that interact strongly with visible light. The infrared envelope reveals carbon dioxide molecules, molecules that glow brightly in thermal infrared but remain nearly transparent to our eyes. Think of it like looking at a jellyfish underwater. In bright light, you see the dense bell and trailing tentacles compact and clearly defined. But switch to ultraviolet and suddenly the entire creature lights up with bioluminescence, a light extending far beyond its visible boundaries. Same organism, different revelation of its true extent. The nested structure of the comet's atmosphere creates a cosmic Russian doll. At the center lies that elusive nucleus no more than 5.6 kilometers across. Surrounding it, a dense inner coma of dust and mixed gases extends roughly 13,000 kilometers in radius. Beyond that, a much more tenuous but vastly larger envelope of carbon dioxide stretches for hundreds of thousands of kilometers, detectable only in specific infrared wavelengths. Each layer tells a different part of the comet's story. The inner optical coma reveals how dust and gas interact near the nucleus. This is where sublimation rates are highest and particle densities are substantial. This region undergoes rapid evolution as solar heating changes. It develops the jets, spirals, and asymmetries that make comet photography so compelling. The outer carbon dioxide envelope operates on much larger scales and longer time scales. Gas molecules in this region have been traveling outward from the nucleus for days or weeks. they expand and cool as they move through the vacuum of space. Their low density makes them invisible to optical telescopes, but bright in infrared wavelengths, where carbon dioxide's molecular vibrations produce characteristic emission lines. JWST's spectroscopic observations reveal additional complexity within this infrared envelope. Water ice grains less than 1 micrometer across scatter short wavelength infrared light. This creates a third component to the comet's multi-layered atmosphere. These tiny crystals probably condense from water vapor in the cold outer regions of the coma. The wavelength-dependent size measurements create communication challenges. Headlines proclaiming 3 Atlas as half the Sun's width are technically accurate, but they are potentially misleading if readers assume this refers to the solid comet itself. The distinction between nucleus coma and extended atmosphere requires careful explanation. This measurement complexity reflects a broader truth about astronomical objects. They rarely have single, well-defined sizes. Galaxies appear different in optical light versus radio waves. Stars have photospheres, chromospheres, and coronas extending to vastly different distances. Planets have solid surfaces, atmospheres, and magnetospheres. 3 Atlas pushes this concept to an extreme. The ratio between its nuclear diameter and its carbon dioxide envelope spans 5 orders of magnitude. That's roughly the same as comparing a marble to the state of Texas. No other object in our solar system demonstrates such a dramatic range of characteristic scales. The evolution of these nested structures provides crucial information about the comet's internal composition and thermal properties. As the comet approaches, perihelion increased, solar heating should expand both components, but potentially at different rates if the nucleus composition is layered. Ground-based observatories face particular challenges when imaging 3 Atlas. The comet's trajectory carries it through the most star-crowded regions of our sky. This requires careful background subtraction and image processing. The size dichotomy also affects how we understand the comet's interaction with the solar wind. The optical coma defines the dense plasma environment, but the extended carbon dioxide envelope determines the overall cross-sectional area for solar wind interaction. This influences tail formation and space weather effects across a much larger volume. Amateur astronomers can contribute to monitoring both size scales. With modest telescopes, they can track changes in the optical coma. Larger instruments might detect portions of the extended infrared envelope. What emerges from this tale of 2 sizes is a lesson about the importance of multi-wavelength astronomy. Each part of the electromagnetic spectrum reveals different physical processes, different spatial scales, and different time evolution patterns. 3 Atlas isn't uniquely large or uniquely small. It's uniquely complex, with characteristic dimensions spanning 5 orders of magnitude, depending on what you're measuring and how you're measuring it. The geometry that magnifies effects, orbital mechanics, can be surprisingly personal. The precise trajectory of 3 Atlas reads like a cosmic itinerary. An itinerary designed to maximize both scientific opportunity and dramatic potential. This isn't random wandering. It's a carefully choreographed dance between gravity and velocity. A dance that will showcase interstellar comet physics under the most revealing conditions possible. The numbers tell the story. An orbital inclination of 175 degrees means 3 Atlas is moving retrograde. It's traveling in the opposite direction from planetary motion. More importantly, it's nearly coplanar with the ecliptic. This combination creates the worst possible traffic pattern, a cosmic head-on collision course with the entire architecture of our solar system. The encounter sequence reads like a planetary tour gone wrong. Mars at 0.19 astronomical units on October 3rd, close enough that the red planet's gravity will measurably deflect the comet's trajectory. Perihelion at 1.36 astronomical units on October 29th. This places 3 Atlas between Earth and Mars at its closest approach to the Sunday, Venus at 0.65 astronomical units on November 3rd, Earth at 1.8 astronomical units on December 19th, Jupiter at 0.36 astronomical units on March 16, 2026. Each encounter represents more than just a close flyby. These are opportunities for gravitational physics and plasma interaction studies. Opportunities that occur perhaps once per century for any given comet. The retrograde geometry means 3 Atlas will be moving at maximum relative velocity. This compresses observation windows, but maximizes the drama of gravitational interactions. The near-ecliptic trajectory carries profound implications for the comet's interaction with the solar wind. The ecliptic plane isn't just where planets orbit, it's also where the solar wind's most complex dynamics play out. The heliospheric current sheet oscillates around the ecliptic. This vast boundary is where the sun's magnetic field changes polarity. Most comets spend relatively little time near the current sheet, but 3 Atlas will cruise along this magnetic boundary for months. It will repeatedly cross between regions of opposite magnetic polarity. Each crossing is a potential trigger for tail disconnection events and plasma instabilities. The geometry also explains why 3 Atlas will be so difficult to observe from Earth. Solar conjunction occurs when the comet passes nearly behind the Sun from our perspective. This makes ground-based observations impossible during the period of maximum activity. This is astronomy's equivalent of Murphy's Law. The most interesting events often occur when we're least able to observe them. But the retrograde trajectory creates unique opportunities elsewhere. Mars orbiters will have an excellent view during the October 3rd flyby. At that time, 3 Atlas will reach magnitude 11 as seen from the red planet. That's bright enough for detailed imaging and spectroscopy. The speed implications are staggering. At perihelion, 3 Atlas will be moving 68 kilometers per second relative to the Sunday fast, enough to cross the continental United States in 90 seconds. Coordinated observation campaigns must account for this velocity. Miss your timing window by a few hours and the comet will have moved significantly. Jupiter's encounter in March 2026 offers perhaps the most valuable opportunity. By then, 3 Atlas will be far from perihelion. It will be moving through a very different solar wind environment. High-speed streams and corrotating interaction regions dominate the outer solar system's space weather. They create conditions that might trigger different types of plasma phenomena. The orbital geometry also affects how the comet's dust and ion tails develop. Dust tails point away from the Sun due to radiation pressure. Ion tails align with magnetic field lines in the solar wind. The retrograde motion means these tails will sometimes point in dramatically different directions. This creates the distinctive forked appearance that makes comets photogenic. Navigation and tracking present unique challenges for such a fast-moving target. Ground-based telescopes must continuously update their pointing to follow the comet. This often results in streaked images that complicate measurements. Space-based observatories like Hubble and JWST face similar tracking difficulties. They require special observation modes designed for moving targets. The near-ecliptic geometry maximizes the comet's time within the interaction region. This is the volume of space where planetary magnetospheres and the solar wind create complex dynamics. Most comets spend only brief periods in this region, but 3 Atlas will cruise through it for more than a year. Amateur astronomers face their own geometric challenges. The comet's path through crowded Milky Way starfields makes identification difficult. The retrograde motion means 3 Atlas appears to move backward relative to most celestial objects. This can potentially confuse observers. Spacecraft mission planners have studied the possibility of redirecting existing probes, but the geometric constraints prove nearly impossible to overcome. The high relative velocities and retrograde trajectory would require enormous fuel expenditures. This places such missions beyond current technological capabilities. What emerges from this geometric analysis is an appreciation for how orbital mechanics amplifies scientific opportunity. The trajectory of 3 Atlas isn't just a path through space. It's a prescription for maximum interaction with every component of our solar system. The same geometry that makes observations challenging also makes them uniquely valuable, providing data that might not be obtainable for centuries. The observing armada. When an interstellar visitor arrives, humanity responds with everything we've got. The observational campaign targeting 3 Atlas represents the largest coordinated study of a single comet in history. It marshals ground-based telescopes, space observatories, and citizen scientists into a unified effort. An effort to extract every possible piece of information before this wanderer disappears forever. JWST leads the charge with its near-infrared spectrograph. It dissects the comet's coma across multiple wavelengths that reveal different chemical components. At 1.2 micrometers, the telescope maps dust distribution. At 2.7 micrometers, water vapor emissions paint a picture of H2O production rates. The 4.3 micrometer band traces carbon dioxide, the dominant component, while 4.7 micrometers reveals carbon monoxide signatures. These JWST observations represent far more than pretty pictures. Each wavelength band corresponds to specific molecular vibrations that encode information about temperature, density, velocity, and composition. The spectroscopic data allows astronomers to construct 3-dimensional maps of chemical abundance, essentially performing a dissection of interstellar ice chemistry. SPHEREX complements JWST's detailed point observations with wide-field mapping. This space-based survey telescope traced the carbon dioxide envelope to its current limit, a limit of a 348,000 kilometer radius. It revealed that the detectable atmosphere extends far beyond optimistic theoretical predictions. SPHEREX also identified water ice absorption signatures. This indicates that solid particles throughout the coma continue to change as they expand outward. The Hubble Space Telescope brings its legendary sharp vision to bear on the comet's innermost regions. It attempts to resolve nuclear structure and constrain the solid body size. These observations push Hubble's capabilities to their limits. They require sophisticated image processing techniques to separate the faint nucleus from the bright coma. The resulting 5.6 kilometer upper limit on nucleus diameter is a remarkable achievement, one of the most challenging small object measurements Hubble has ever attempted. Ground-based observatories face unique challenges when targeting 3 Atlas. The comet's trajectory carries it through the densest star fields visible from Earth. This requires careful background subtraction and field identification. Gemini North's 8-meter mirror provides the light-gathering power necessary for detailed spectroscopy. It monitors how the comet's composition and activity levels evolve as solar heating increases. The amateur astronomy community has embraced 3 Atlas with great enthusiasm. The Virtual Telescope Project and similar citizen science networks provide crucial cadence observations. They track morphological changes and brightness variations that complement professional campaigns. These amateur contributions are especially valuable for monitoring rapid changes that might occur between scheduled professional observations. Coordination between observatories requires unprecedented precision. The high velocity of 3 Atlas means that observation timing must be synchronized to within hours. This ensures that different telescopes are studying the same physical phenomena. Target of opportunity scheduling allows observatories to respond quickly to unexpected changes. But coordinating such responses across multiple institutions presents logistical challenges. The multi-wavelength approach reveals different aspects of the comet's complex environment, Ultraviolet observations will probe atomic emissions from the innermost coma. Optical wavelengths trace dust scattering and certain molecular emissions. Near-infrared reveals thermal emission from warm dust and major gas species. Radio observations might detect exotic molecules present in trace abundances. Data processing and analysis present their own challenges. Each observatory uses different instruments and calibration procedures. This requires careful cross-calibration to ensure measurements can be meaningfully compared. The International Astronomical Union coordinates standards for comet observation reporting, but the unusual properties of 3 Atlas sometimes push beyond established conventions. NASA's Planetary Defense Coordination Office serves as a central clearinghouse. It collects and disseminates updates from participating observatories. This coordination is essential for maintaining public confidence in scientific conclusions. It ensures that preliminary results undergo appropriate peer review before reaching the news, and it avoids the kind of sensationalized reporting that sometimes accompanies unusual discoveries. The observational Armada scope extends beyond traditional astronomical facilities. Mars orbiters might attempt observations during the October 3rd flyby. This could potentially provide our first direct spacecraft measurements of an interstellar comet's plasma environment. These observations would complement remote sensing data with in-situ measurements impossible to obtain from Earth-based telescopes. Communication of results requires careful attention to uncertainty and to the difference between preliminary and final conclusions. Astronomical observations typically undergo months or years of analysis before publication, but public interest in 3 Atlas creates pressure for rapid result dissemination. Preprint servers allow researchers to share preliminary findings, but news media sometimes report these early results as definitive conclusions. The citizen science component extends beyond amateur telescope observations. It includes computational contributions as well. Projects like distributed computing networks can assist with data processing and analysis, while online collaboration platforms allow amateurs to contribute to morphology monitoring. These contributions demonstrate how modern astronomy increasingly relies on community participation. What emerges from this coordinated campaign is a new model, a model for studying rare astronomical phenomena. Rather than relying on serendipitous observations, 3 Atlas has prompted a systematic collaborative approach, an approach that maximizes scientific return from fleeting opportunities. This template will prove invaluable when future interstellar objects arrive. It ensures that humanity is ready to extract maximum scientific value from each cosmic visitor. The observational Armada targeting 3 Atlas represents more than just telescope time. It's a demonstration of how modern astronomy operates as a global enterprise, combining cutting-edge technology with international cooperation and citizen participation, all to answer fundamental questions about our place in the galaxy. Space weather, what to expect. Solar maximum has arrived, and 3 Atlas couldn't have picked a better time to visit. Our Sun is approaching peak activity in its 11-year magnetic cycle. It's spawning coronal mass ejections and high-speed wind streams, and the kind of chaotic magnetic field conditions that transform comet tails, transforming them from gentle streamers into spectacular displays of celestial violence. But let's be absolutely clear about cause and effect. 3 Atlas didn't trigger solar maximum, and solar maximum isn't responding to 3 Atlas. The Sun operates on its own magnetic schedule, completely indifferent to whatever visitors happen to be passing through. What we're witnessing is pure cosmic coincidence, an ancient interstellar wanderer arriving just as our star enters its most temperamental phase. The timing creates unprecedented opportunities for studying comet plasma physics under extreme conditions. Coronal mass ejections occur several times per week during solar maximum, These are billion-ton blobs of magnetized plasma hurled from the Sun. When one of these magnetic monsters slams into the comet's extended atmosphere, the results should be spectacular. We may see compressed Comet restructured tails and possibly complete tail disconnection events. This happens as magnetic field lines snap and reconnect with explosive force. Historical precedents exist for such space weather interactions. Comet McNaught in 2007 experienced dramatic tail disconnections. This created images that looked more like cosmic lightning bolts than gentle streamers. 3 Atlas could produce even more dramatic displays. With its massive atmosphere and proximity to solar maximum conditions, the physics underlying these interactions reads like a textbook on plasma instabilities. When a CME's magnetic field encounters the comet's ionized coma, the two don't merge smoothly. Instead, they undergo magnetic reconnection, a process where opposing field lines break and reform, releasing enormous amounts of energy. This energy heats plasma to millions of degrees, and it accelerates ions to velocities approaching 1% of light speed. The orbital geometry of 3 Atlas amplifies these space weather effects. The comet's near-ecliptic trajectory means it will spend months cruising along the heliospheric current sheet, a vast wavy boundary where the Sun's magnetic field reverses polarity. Most comets cross this boundary quickly, but 3 Atlas will repeatedly encounter regions of opposite magnetic polarity. This creates multiple opportunities for dramatic plasma interactions. The European Space Agency's Rosetta mission provided our first intimate view of these effects. Even the quiet Comet 67P showed remarkable sensitivity to solar wind variations. Its plasma densities and magnetic fields fluctuated dramatically in response to minor changes. 3 Atlas with activity levels orders of magnitude higher should amplify these effects proportionally. Current sheet crossings deserve particular attention. They often coincide with stream interaction regions. These are boundaries between fast and slow solar wind that create compression waves. These regions can dramatically alter the pressure and magnetic field strength surrounding the comet. They could potentially trigger sudden changes in coma morphology visible from Earth. Visual signatures of space weather interactions appear across multiple wavelengths. Ultraviolet emissions spike when magnetic reconnection heats plasma in the inner coma. Optical images reveal kinks, rays, and disconnections in the tails. This is as they respond differently to magnetic forces versus radiation pressure. Radio emissions might spike as accelerated particles generate plasma waves. The distinction between dust and ion tails becomes crucial during these events. Dust particles respond primarily to photon pressure from sunlight. They create tails that point steadily away from the Sun. Ion tails, composed of electrically charged gas coupled directly to magnetic field lines. They can swing dramatically as those fields change orientation during a CME passage. Mars orbiters might provide our first direct measurements of how 3 Atlas affects planetary space weather. This would be during the October 3rd encounter. If the red planet passes through the comets, plasma wake instruments could detect changes in the planetary ionosphere or magnetosphere impossible to observe from Earth. Predictions for specific space weather events remain necessarily vague. This is because solar activity follows chaotic rather than predictable patterns. We can estimate statistical probabilities, perhaps a 50% chance of at least one major CME encounter, but precise timing predictions exceed our current forecasting capabilities. Amateur astronomers can contribute to space weather monitoring. They can rapidly report sudden changes in the comet's tail morphology or brightness. These observations provide crucial real-time data that professional observatories might miss. Citizen science networks have proven particularly effective at monitoring such transient phenomena. The heliospheric current sheet structure varies with the solar cycle. It becomes more warped and complex during solar maximum. This increased complexity creates more opportunities for 3 Atlas to encounter magnetic field reversals, but it also makes the specific geometry of each encounter more difficult to predict. The comet's path will depend on the detailed magnetic field configuration at the time. Educational opportunities abound for explaining space weather concepts using 3 Atlas. The comet's interactions provide concrete examples of plasma physics principles. Visual evidence of magnetic reconnection and plasma acceleration makes these processes accessible to general audiences. What we must avoid is ascribing agency or intent to natural processes. 3 Atlas doesn't cause solar storms any more than a weather vane causes wind. The comet serves as an exquisitely sensitive probe of space weather conditions. It reveals solar wind structures and magnetic field variations that would otherwise remain invisible. It's a scientific instrument disguised as a visitor from another star. The space weather predictions for 3 Atlas read like a cosmic weather forecast. A high probability of magnetic storms, excellent chances for tail disconnection events, and spectacular opportunities for studying plasma physics under the most extreme natural conditions. Conditions our local stellar environment can provide. Science payoffs at terrifying scale. The scientific return from 3 Atlas extends far beyond simple comet characterization. This ancient wanderer carries information that will reshape our understanding of planet formation and of stellar evolution and the chemical diversity of planetary systems across our galaxy. Every spectrum, every image, every measurement adds another piece to a vast puzzle, a puzzle that spans billions of years and thousands of light years. Interstellar chemistry benchmarking represents the most immediate scientific payoff. The extreme carbon dioxide to water ratio of 3 Atlas 8:1 establishes a new endpoint, an endpoint for comet composition diversity. Previous observations suggested water-dominated chemistry was universal among comets, but 3 Atlas proves that assumption catastrophically wrong. The 6 sigma deviation from normal comet chemistry isn't just unusual, it's revolutionary. It forces a complete revision of models for ice condensation in protoplanetary disks. The implications cascade through planetary science. If 3 Atlas represents a typical composition for comets forming far out, then planetary systems might be different. Systems around other stellar types might show radically different volatile inventories. M-dwarf stars, which comprise 75% of all stars, create very different environments. 3 Atlas might be our first direct sample of M-dwarf system chemistry. Dusty plasma physics receives an unprecedented natural laboratory through the comet's enormous coma. The half-sun-wide atmosphere operates as a particle accelerator and plasma physics experiment. An experiment on scales impossible to reproduce artificially. Magnetic field interactions, dust charging processes, and ion acceleration mechanisms studied here will inform other research. From fusion reactor design to interstellar medium modeling, the Rosetta mission provided detailed measurements around a relatively quiet comet, but 3 Atlas offers the opportunity to study these processes at extreme activity levels. Ion densities and magnetic field strengths should exceed anything measured at Churyumov-Gerasimenko. This will push plasma physics models into unexplored territory. Formation constraint studies using the comet's chemical fingerprint will help calibrate models of protoplanetary disk evolution around different stellar types. The carbon dioxide dominance suggests either formation at very large distances from the host star, or exposure to intense stellar irradiation that preferentially removed water. Each scenario implies different conditions in the birth stellar system. Formation at large distances requires protoplanetary disks more massive and extended than typical models predict. Irradiation processing demands proximity to luminous stars. Both possibilities expand the range of environments where comet formation might occur. This increases estimates for interstellar object populations throughout the galaxy. Galactic archaeology benefits enormously from the likely thick disk origin of 3 Atlas. Objects with ages exceeding 7 billion years sample stellar formation conditions from an earlier time, a time when our galaxy was younger, more chaotic, and chemically distinct. The comet's composition preserves isotopic ratios and elemental abundances from this ancient environment. This provides direct constraints on galactic chemical evolution models. Thick disk populations formed during an era when stellar metallicity was significantly lower. Metallicity is the abundance of elements heavier than hydrogen and helium. If 3 Atlas truly represents this ancient population, its composition should reflect that. Consistent with nucleosynthesis models for early galactic evolution, interstellar object population statistics receive crucial calibration data from every confirmed detection. 3 Atlas combined with Oumuamua and Borisov establishes the beginning of a statistical sample, a sample that constrains models for how often stellar systems eject debris. Current estimates suggest every star system loses thousands to millions of small bodies. This creates a galaxy-wide population of wandering objects numbering in the quintillions. The chemical diversity observed across just 3 interstellar objects is enormous. Oumuamua's possible water ice, Borisov's carbon monoxide enhancement, and the carbon dioxide dominance of 3 Atlas. This suggests enormous variety in formation conditions across different stellar systems. This diversity challenges simple models of planetary system architecture. Comparative planetology expands to truly comparative scales through these studies. Rather than comparing planets within our single stellar system, we can now compare formation products from completely different stellar environments. 3 Atlas represents data from what might be an M-dwarf system or a binary star environment, or a stellar nursery, with very different properties than where our Sun formed. Methodology development for rapid interstellar object characterization will benefit future discoveries. The Coordinated Observational Campaign for 3 Atlas established protocols for international telescope coordination, data sharing, and rapid response spectroscopy. These will streamline studies of future visitors. These techniques become increasingly important as next-generation surveys begin detecting dozens per year. Public engagement through 3 Atlas demonstrates astronomy's unique ability to capture popular imagination. The comet's dramatic scale interstellar origin and spectacular space weather interactions provide natural hooks for science communication, inspiring the next generation of researchers, and for building public support for astronomical research programs. Astrobiology implications emerge from the comet's chemical composition. If carbon dioxide-rich ices are common in other stellar systems, they might provide different delivery pathways for delivering volatiles to forming terrestrial planets. The carbon-rich chemistry could support different types of prebiotic chemistry, different from the water-dominated models typically considered for early Earth. The scientific payoffs from 3 Atlas operate across multiple scales, from the fundamental physics of plasma interactions to galactic-scale models of chemical evolution. This single interstellar visitor carries information that would be impossible to obtain through any other means. We're not just studying a comet. We're conducting a comprehensive survey of conditions in an alien stellar system, a system preserved in ice and delivered directly to our doorstep after a billion-year journey. Comparisons 1 Oumuamua and 2 Borisov. The Interstellar Object Hall of Fame consists of exactly 3 members, and they couldn't be more different from each other, as if they had been designed by a committee to showcase the full range of cosmic possibilities. Each represents a completely different class of object, formation, environment, and evolutionary pathway. Collectively, they paint a picture of galactic debris so diverse it challenges every assumption about planetary system architecture. First came Oumuamua in 2017, the astronomical equivalent of a first contact that left everyone more confused than enlightened. This cigar-shaped wanderer showed no detectable coma, no gas production, and no obvious comet-like behavior. Despite following a clearly hyperbolic trajectory, its extreme elongation, unusual acceleration, and tumbling rotation created a mystery that remains unsolved nearly 8 years later. Theories proliferated like academic mushrooms after rain. Was Oumuamua a fragment of a tidally disrupted asteroid, a shard of exotic ice that sublimated invisibly? Some researchers even suggested it might represent our first encounter with extraterrestrial technology, a hypothesis that generated tremendous public interest but found little support in the data. The Oumuamua controversy highlighted both the excitement and the dangers of studying these objects. With limited observation windows and unprecedented phenomena, the line between science and sensationalism can become thin. The object's rapid departure ensured that many questions would remain permanently unanswered. This left room for speculation that continues today. Then came Borisov in 2019. Arriving like a cosmic palate cleanser after Oumuamua's confusion, here was an object that behaved exactly as astronomers expected. An interstellar comet with obvious coma development and predictable gas production, and spectroscopic signatures that screamed dirty snowball from space. Borisov restored confidence in our understanding of comet physics. It demonstrated that interstellar objects could be studied using conventional techniques. But Borisov carried its own chemical surprises. Spectroscopic observations revealed unusually high carbon monoxide abundances, not as extreme as 3 Atlas, but still significantly enhanced compared to typical comets. The CO-rich composition suggested formation in a colder environment than most solar system objects, hinting at different thermal conditions in Borisov's birth stellar system. Borisov's nucleus remained more conventional in size estimates, probably a few kilometers across based on brightness modeling. Its activity levels, while high, didn't approach the extreme gas production rates of 3 Atlas. Borisov represented interstellar chemistry that was unusual but not revolutionary. The visibility timeline favored Borisov enormously compared to 3 Atlas. The comet remained observable for months from Earth-based telescopes. This allowed detailed monitoring of its evolution. Amateur astronomers could contribute meaningful observations. This created a citizen science campaign that engaged thousands of observers worldwide. Now 3 Atlas arrives to complete this bizarre trilogy. It brings chemistry so extreme, it makes Borisov look conventional by comparison. The 8:1 carbon dioxide to water ratio pushes comet composition into new territory. It challenges basic assumptions about ice condensation in protoplanetary disks. Where Oumuamua was mysteriously inactive and Borisov was reassuringly normal, 3 Atlas is hyperactive in completely unexpected ways. The velocity comparisons reveal the dynamic diversity of interstellar space. Oumuamua approached at roughly 26 kilometers per second. Borisov moved at about 32 kilometers per second. 3 Atlas screams through our solar system at 58 kilometers per second, making it the fastest yet. Orbital geometries paint 3 completely different pictures of galactic dynamics. Oumuamua followed a steep, highly inclined trajectory. This minimized its interaction time with planetary and solar wind structures. Borisov's orbit was moderately inclined, providing reasonable observation opportunities. The path of 3 Atlas represents the most dynamically interesting case. It has maximum interaction time with solar wind structures and multiple planetary encounters. This geometry alone makes 3 Atlas scientifically valuable, regardless of its unusual chemistry. The nucleus size constraints span an enormous range across all 3 objects. Oumuamua's dimensions were inferred from its extreme brightness variations. It was likely between 100 and 1,000 meters in length. Borisov's nucleus appeared to be a few kilometers across. 3 Atlas pushes nuclear size uncertainty to its limits. Its 5.6-kilometer upper bound could accommodate objects as small as a few hundred meters. The disconnect between nuclear size and activity level reaches its most extreme expression with 3 Atlas. A potentially tiny solid body generates an atmosphere comparable to stellar dimensions. Public narrative evolution across the 3 discoveries reveals how astronomical communication has adapted. Oumuamua sparked wild speculation about alien artifacts, partly because scientists were appropriately cautious with limited data. Media and social media filled the uncertainty vacuum with exotic explanations. Borisov benefited from lessons learned. Scientists communicated more proactively about what the observations revealed, emphasizing the comet's conventional behavior while highlighting its interesting chemistry. The result was more balanced coverage that maintained public interest without unfounded speculation. 3 Atlas represents the newest test case for science communication in the social media era. The comet's extreme properties provide natural hooks for public engagement, while requiring careful explanation to distinguish genuinely unusual science from science fiction. Comparative analysis across all 3 interstellar visitors reveals the importance of statistical samples. Any single object might represent an extreme outlier, but 3 objects showing such diverse properties strongly suggest something else. That interstellar space contains representatives of every possible formation environment. The chemical progression from Oumuamua through Borisov to 3 Atlas maps out a continuum of compositions. This diversity confirms theoretical predictions that interstellar objects sample the full range of small body types. What emerges from comparing our 3 confirmed interstellar visitors is a lesson about making generalizations from limited data. Each object has confounded expectations in different ways. This suggests that our 4th, 5th, and 6th interstellar discoveries will probably surprise us just as thoroughly. The galaxy appears to contain small body populations far more diverse than our single stellar system suggested. The interstellar object comparison also highlights the value of rapid response observational capabilities. Oumuamua was discovered too late for optimal characterization. Borisov received better coverage but still departed before many observations could be completed. 3 Atlas represents our best opportunity yet to study an interstellar visitor throughout its entire encounter. As we await the next interstellar visitor, the 3 confirmed objects provide a foundation for understanding what kinds of debris wander between the stars, and what they can tell us about planetary system formation throughout our galaxy. Each visitor carries messages from stellar neighborhoods so distant their light hasn't reached us yet, making interstellar objects our fastest and most direct method for studying the chemical diversity of alien worlds. What will watch through 2026? The next 18 months will unfold like a carefully choreographed cosmic ballet, with 3 Atlas pirouetting through our solar system, while humanity's most sophisticated instruments document every twist, every leap, every moment. The timeline reads like a greatest hits album of astronomical opportunities, each encounter offering unique scientific prospects that may not repeat for centuries. October 3, 2025 marks the opening act. A Mars flyby at 0.19 astronomical units, roughly 19 million kilometers. From the red planet's perspective, 3 Atlas will blaze at magnitude 11, bright enough for detailed imaging if Mars orbiters can be convinced to look up. The European Space Agency's Mars Express and NASA's MAVEN carry capable instruments. They offer our first chance at in-situ measurements of an interstellar visitor's interaction. The Mars encounter geometry creates opportunities for triangulation observations, with Earth-based telescopes and Mars orbiters simultaneously viewing from different angles. These parallax measurements could help resolve the persistent uncertainty about nucleus size. They provide independent constraints that don't rely on albedo assumptions. Solar conjunction looms as the performance reaches its climax. October 29th, perihelion places 3 Atlas at its closest approach to the Sun. Gas production should reach maximum intensity and the coma should expand to its largest extent. Unfortunately, the geometry conspires against Earth-based observers. It positions the comet nearly behind the Sun from our perspective. This makes ground-based observations impossible during the most interesting period. But space-based telescopes don't suffer from solar glare. Hubble has planned ultraviolet observations designed to probe atomic emissions. Emissions in the innermost coma, where collision-induced fluorescence reveals information about gas densities and temperature distributions. These UV measurements will complement earlier infrared spectroscopy. They will build a comprehensive picture of the comet's atmospheric structure. The post-perihelion observation campaign of JWST promises the most detailed chemical analysis in history. As 3 Atlas emerges from solar conjunction in November, the telescope will repeat its measurements. It will monitor how gas production rates and compositional ratios change. These comparisons will reveal if the extreme carbon dioxide dominance is intrinsic to the nucleus, or if it results from preferential release due to surface effects. The geometry of Venus on November 3rd offers yet another planetary encounter, though at a more comfortable distance of 0.65 astronomical units. The encounter occurs in a different solar wind sector than the Mars flyby, potentially exposing 3 Atlas to different magnetic field orientations. December 19th brings the comet's closest approach to Earth, at 1.8 astronomical units, still more than the Sun's distance, but close enough for coordinated ground-based campaigns using the world's largest telescopes. By then, 3 Atlas will have survived perihelion and begun its outbound journey, allowing astronomers to study how the coma contracts and evolves. The Earth encounter timing coincides with excellent observing geometry for Northern Hemisphere telescopes, potentially enabling amateur astronomical communities to contribute meaningful observations. Citizen science networks have already begun preparing finder charts and observation protocols, hoping to engage thousands of observers in monitoring the comet's post-perihelion behavior. March 16, 2026, delivers the finale, a Jupiter encounter at 0.36 astronomical units. By then, 3 Atlas will be operating under very different conditions. The outer solar system's space weather is dominated by high-speed wind streams, not the coronal mass ejections that characterize the inner heliosphere. Jupiter's enormous magnetosphere creates additional complexity for the encounter. If 3 Atlas passes through the Jovian magnetic field, its plasma tail could undergo dramatic restructuring. These interactions might be observable from Earth as sudden changes in tail morphology. Spacecraft mission concepts continue evolving as the trajectory becomes better defined, while no existing missions can be redirected to intercept the comet. Feasibility studies will benefit. Studies for future interstellar object encounters will benefit from the challenges 3 Atlas presents. The lessons learned will inform planning for rapid response missions to future visitors. The extended observation timeline allows monitoring of processes that operate on different timescales. Nucleus rotation might reveal shape and spin state information. Coma morphology evolution traces the response of gas and dust production to changing solar illumination. Tail disconnection and reconnection events respond to solar wind variations on timescales of hours to days. Data release schedules from major observatories ensure that scientific results will continue emerging long after 3 Atlas departs our solar system. JWST observations typically require months of processing and analysis. Hubble's UV spectroscopy involves complex calibration procedures that can extend timelines. Ground-based campaigns often rely on coordinated data sharing that can take months to organize. The Minor Planet Center continues issuing updated orbital elements as new observations arrive. These updates are crucial for planning future observations. They ensure that telescope pointing remains accurate as the comet's high velocity carries it rapidly. Amateur astronomers and professional observatories alike depend on these ephemeris updates. Public engagement activities will track 3 Atlas throughout its solar system passage, with astronomy education organizations planning special events around each major encounter. The comet's interstellar origin and extreme properties provide natural hooks for discussion, discussing topics ranging from stellar evolution to plasma physics, potentially inspiring a new generation of scientists and maintaining public interest. Archive observations will continue contributing to the science of 3 Atlas long after it disappears. Digital sky surveys have been imaging the comet's path for months before its discovery. Careful analysis of these archival data might reveal earlier stages of Comet development. These recovery observations extend our baseline for understanding how the comet's activity evolved. The 18-month observation campaign represents humanity's most comprehensive study of any single comet. By the time 3 Atlas accelerates back into the void, we will have accumulated more detailed measurements, more than any previous mission or observation campaign has achieved. The data will be analyzed and reanalyzed for decades, ensuring that this ancient visitor's brief appearance continues, yielding scientific discoveries long after it's gone. The real meaning of terrifying scale. As 3 Atlas accelerates toward its final departure, we're left to contemplate something. What does terrifying scale really mean? An age when the universe reveals new impossibilities with each advancing year. Physical scale first. That gossamer atmosphere stretching 696,000 kilometers across space, wrapping half the sun's diameter around a nucleus smaller than most asteroids. The ratio defies earthly intuition. It's like discovering a marble can generate a fog bank the size of Texas, or that a single grain of sand can cast shadows across entire continents. 3 Atlas forces us to recalibrate our understanding of how small objects can influence vast regions of space. The Comet's enormous extent creates interaction cross-sections with the solar wind that exceed our experience. When coronal mass ejections encounter 3 Atlas, they're hitting a target area comparable to a small star. Even though the source of all this drama measures less than Manhattan's width, the physics scales up. It scales in ways that challenge our ability to model or predict, pushing plasma simulations into regimes no laboratory could ever reproduce. Dynamical scale demands equal attention. 68 kilometers per second at perihelion, fast enough to cross the United States in less than 2 minutes. This isn't the leisurely orbital mechanics of planets or familiar comets. 3 Atlas moves with the desperate urgency of an object that has already escaped the sun's gravity. An object that seeks only to minimize its time in alien territory. The velocity carries implications that extend far beyond simple numbers. At such speeds, 3 Atlas experiences our entire solar system as a brief interruption. An interruption in its billion-year journey through interstellar space. The 18 months from discovery to departure represent perhaps 1/1,000,000th of its total travel time. We're witnessing the cosmic equivalent of a highway rest stop, a momentary pause in an odyssey that spans geological time. Temporal scale provides perhaps the most unsettling perspective of all. Multiple analyses suggest 3 Atlas belongs to our galaxy's thick disk population. This implies an age exceeding 7 billion years. This wanderer may have formed when our solar system was nothing more than a diffuse nebular cloud. It carries chemical fingerprints from an epoch when star formation followed different rules. The comet has witnessed our galaxy's evolution through cosmic epochs we can barely imagine. It survived whatever catastrophe ejected it from its birth system, perhaps a stellar flyby, planetary instability, or the death of its parent star. It cruised through the void while our sun condensed, while planets formed, while life arose on Earth. Yet for all its ancient heritage, 3 Atlas demonstrates incredible electromagnetic vitality. That half-sun-wide atmosphere isn't just expanding gas. It's a living, breathing plasma environment where magnetic fields twist and reconnect, where particles accelerate to incredible velocities, where the gentle pressure of starlight sculpts matter across vast distances. The plasma physics playing out around 3 Atlas operates on scales that humble human engineering. Magnetic field lines stretch and snap across volumes that could contain multiple Earth orbits. Electric fields build up and discharge with energies that make terrestrial lightning look like static. Ion acceleration proceeds continuously across the entire coma, creating a natural particle accelerator that dwarfs anything we could construct on Earth. Solar maximum timing amplifies every dramatic possibility. 3 Atlas arrived not during a quiet solar minimum, but during our star's most tempestuous phase. Coronal mass ejections and magnetic field reversals create a chaotic plasma environment, an environment that transforms predictable comet tails into spectacular displays of cosmic violence. The observational challenges match the physical extremes. 3 Atlas crosses the most star-crowded regions of our sky. It requires careful separation of comet light from the dense stellar background. Its rapid motion streaks telescope images. Its enormous coma confounds traditional photometry, and its interstellar chemistry resists easy interpretation. Each measurement pushes instrumental capabilities toward their limits. Hubble's nucleus size constraint is one of the most challenging small object observations ever attempted. JWST's spectroscopic analysis ventures into compositional territory no previous mission has explored. SphereX coma mapping required extending detection algorithms beyond their original design. The scientific implications cascade across multiple disciplines. 3 Atlas isn't just an unusual comet. It's a direct sample of interstellar chemistry, a probe of ancient galactic conditions, and a natural laboratory for studying plasma physics under extreme conditions. Every measurement constrains models of planet formation around other stars, while revealing new complexities in processes we thought we understood. But perhaps the most terrifying scale of all is the scale of our ignorance. An ignorance illuminated by the visit of 3 Atlas. This single object has revealed gaps in our understanding of comet chemistry, plasma physics, and galactic evolution, gaps that will require decades of additional research to address. It demonstrates how much we still don't know about the universe beyond our immediate stellar neighborhood. 3 Atlas forces us to confront a possibility. The possibility that our solar system represents just one example of planetary system architecture. In a galaxy containing billions of alternatives, the extreme chemistry, unusual dynamics, and ancient heritage of this visitor suggests something profound, that the cosmos harbors phenomena far stranger and more diverse than our provincial experience has prepared us for. When 3 Atlas finally disappears into the void, it will carry with it our measurements, our curiosity, and our humility in the face of cosmic scales that exceed human comprehension. The terrifying scale isn't just about size, speed, or age. It's about the revelation that the universe continues operating at extremes. Extremes that challenge our most basic assumptions about what's possible. In the end, 3 Atlas serves as a reminder that we inhabit a cosmos where ancient wanderers can carry messages across billions of years, where tiny objects can generate phenomena on stellar scales, and where the space between the stars isn't an empty void, but a vast ocean of possibilities. an ocean we've barely begun to explore. The comet's brief visit leaves us with questions that will outlive everyone currently studying it, ensuring that its legacy extends far beyond its physical departure. Sometimes the most profound discoveries come from encountering phenomena so extreme, they force us to expand our definition of what the universe allows. And in that expansion of possibility lies both terror and wonder. The recognition that we live in a cosmos far stranger, more violent, and more magnificent than our earthbound experience could ever suggest.